Hello viewers! Welcome to Operations Research 1 tutorial video. I'm KJ.
I'm Elmer.
And I'm Zyra. In this another tutorial video, we are going to show you how to solve transportation algorithm, assignment method, and network algorithms. The assignment problem. The assignment problem deals with assigning machines to tasks, workers to jobs, soccer players to positions, and so on. The goal is to determine the optimum assignment that, for example, minimizes the total cost or maximizes the team effectiveness. The assignment problem is a fundamental problem in the area of combinatorial optimization. So we have here an estimated project repair cost for the fix-it shop assignment problem. The owner's objective is to assign the 3 projects to the workers in a way that will result in the lowest total cost to the shop. Note that the assignment of people to projects must be on a one-to-one basis. Each project will be assigned exclusively to one worker only. So the first step in assignment method is to find the opportunity cost. So first is the row reduction. So we have to subtract the smallest number in each row from every number in that row. So the smallest number in this row is 6. So we have to subtract 6 in each number. So 11 minus 6, 5, 14 minus 6, 8, 6 minus 6, 0. And then do the same thing in the next row. So this will now be the result. From here, the next thing we should do is the column reduction. So we have to subtract the smallest number in each column from every number in that column. So the smallest number in this column is 0. So we have to subtract 0 from each of the number, then the smallest number here, and then here. So this will now be the result from the column reduction. So from here, we are going to do the optimality test. We are going to test opportunity cost table to see if optimal assignments are possible by drawing the minimum possible number of lines on columns and or rows such that all zeros are covered. So we are going to cover here and then here. So this will now be the result of the optimality test. And since the number of lines here is less than the number of columns, we have to revise this opportunity cost table. So first, we have to subtract the smallest number not covered by a line from itself and every other uncovered number. So the number that is smallest from here that is not covered by the line is 2. So we have to subtract 2 in these numbers. So 5 minus 2, 3, 2 minus 2, 0, 6 minus 2, 4, 3 minus 2 is 1. And then we have to add this number at every intersection of any 2 lines. Since the intersection or the number in the intersection here is 3, we have to add 2 to this number. So this will now become to this. And from this revised opportunity cost table, we have to go back to test or the optimality test. Then we have to cover all the lines which has 0. So we have to cover here, this one, and this one. So this will now be the result from the revised opportunity cost table. So when making the final assignment, we have to select a row or column that contains only one 0 cell. So the first cell is in Adam's row. So we have to cover it here. And then here. So from the uncovered rows and columns, we again choose a row or column in which there is only one 0 cell. So that cell will be here. So we have to cover here and then here. And then the last 0 that we have to cover is this one. So these are the assignments of the 3 workers. The total labor cost of these assignments are computed from the original cost table. So from this 0, the cost here is 6. Then from here, the cost here is 10 from the original table. And then from this 0, the original cost is 9. Now have here the assignment of each workers to their project. So Adams to project 3, $6. Brown to project 2, $10. Cooper to project 1 is $9. So the total cost for this project is $25.
The transportation algorithm. The transportation algorithm is an iterative procedure in which an initial solution to a transportation problem is found. Now let's try to have a sample problem of the transportation algorithm. So we will be using the Executive Furniture Corporation example. So the table here shows that the company manufactures office desks at 3 locations. And these locations are the Des Moines, Evansville, and Fort Lauderdale. The firm also distributes the desk through regional warehouses that is located in Albuquerque, Boston, and Cleveland. In each warehouses, we have an estimate of its monthly production capacity. For the Des Moines factory, we have 100 units, Evansville is 300 units, and we also have 300 units for the Fort Lauderdale factory. So we also have a monthly demand in each warehouse. So for warehouse at Albuquerque, we have 300 units, Boston is 200 units, and Cleveland is also 200 units, with a total demand and total supply of 700 units. And the empty cells here represent the source to destination shipping assignment that could be made when we are going to solve the problem. And the small boxes here are the cost of its shipping. Like for example, the $7 is a cost of shipping 1 unit from Fort Lauderdale factory to Boston warehouse. In solving this problem, we will be using the one systematic procedure that is known as the northwest corner rule. So the northwest corner rule requires that we start in the upper left-hand cell or northwest corner of the table and allocate units to shipping routes. Now let's try to solve the problem. First is we will be allocating 100 units from the upper left-hand corner, which is from Des Moines to Albuquerque. So since we've already got the factory capacity of 100 units, we will now be proceeding to the next row. Here, from Evansville to Albuquerque, we just assigned 200 units since we've already meet the warehouse requirements of 300 units. After that, we will be proceeding with the next column since we still have 100 units left. So these 100 units remaining, we will be assigning this one here from Evansville to Boston. After that, we can now proceed with the next row. So here we just assign 100 units here again so that we can meet the warehouse requirements of Boston, which is the 200 units. After that, we still have 200 units remaining of the Fort Lauderdale factory. So here we will be assigning now the 200 units. So since we already meet the warehouse requirements of Cleveland, which is 200 units, we have now a balanced problem, and the initial shipment schedule is now complete. Okay, since we're done with allocating units from the factory to its warehouses, we can now solve its cost. So in solving its cost, we will just multiply the units shipped to its unit cost. Like for example, from D to A. D is the Des Moines and A is Albuquerque. We assigned here or allocate 100 units here and just multiply its unit cost, which is $5. And we've got the $500. So from E to A, which is Evansville to Albuquerque, we have 200 units and multiply its unit cost, which is $8, and we got $1,600 as its total cost. So same procedure in solving with the next routes, like for example E to B, F to B, and F to C. So here E is Evansville and B is Boston, and F is Fort Lauderdale and C here is Cleveland. So after solving the total cost of each route, we will add all of these total costs and we could get $4,200. So now we get that the solution is feasible since the demand and supply constraints are already satisfied. And now we're done with
Shortest route problem, a technique that minimizes the distance through a network. Its goal is to find the shortest path that you can travel from one point to another point in the network. In a network, this often involves determining the shortest route from one node to each of the other nodes. So these are the steps of the shortest route technique. First, find the nearest node to the origin, put the distance in a box by the node. Second step is find the next nearest node to the origin and again, put the distance in a box by the node. But in some cases, several paths will have to be checked to find the nearest node. The third step is to repeat this process until you have gone through all the entire network. The last distance at the ending node will be the distance of the shortest route. You should note that the distance placed in the box by each node is the shortest route to this node. These distances are used as intermediate results in finding the next nearest node. We have a sample problem here. Everyday Ray Design Incorporated must transport beds, chairs, and other furniture items from the factory to the warehouse. This involves going through several cities. Ray would like to find the route with the shortest distance. So shown below is the road network. Looking at the road network, we can see that the nearest node to the plant is node 2, with a distance of 100 miles. Thus, we will connect these two nodes, which is the first iteration. Now we'll look for the next nearest node to the origin. We check nodes 3, 4, and 5. We can see that path 1, 2, 3 is the nearest to the origin, with a total distance of 150 miles. We connect these nodes and we have the second iteration. We repeat the process. The next nearest node is either node 4 or 5. Note that the minimum distances are placed in the red boxes by the shortest route we just got. We can determine that the path from node 5 to the origin through node 3 is 190 miles. 40 miles between node 5 and 3 plus 150 miles from node 3 to the origin. Thus, we've picked node 5 going through node 3 to the origin. This is our third iteration. So going through our fourth iteration, the next nearest node will be either 4 or node 6 as the last remaining nodes. We can determine that node 6 is 290 miles from the origin. Thus, node 6 has the minimum distance, and because it is the ending node, we are done. So now we have our shortest route, which is path 1, 2, 3, 5 through 6, with a minimum distance of 290 miles.
Thank you for watching our video.
You can leave some questions and clarifications under the comment section below.
Please like and share this video.
And don't forget to subscribe.
Bye, viewers!